So now we're focused on finding the particular solution using the forcing function and method of undetermined coefficients. So here's our forcing function, f of t. If you remember the form, that matches with our f of t, which is 40, 0. So given that f of t is the vector 40 and 0, we can say that a good guess for x of p is AB. And since we don't have an e to the 0, we don't have any linear dependence with the complementary solution. So we don't need to do anything funky. We can just use that. And if that's our guess, then x prime of p is going to be 0, 0. So then we can say that the x prime of p is equal to A, which is our matrix -1, 0, and 1, -1. And that's going to be multiplied by A times B plus, and this is the part, I'll do it in a different color. This is the part I always forget. You need to add this, otherwise you guessed a solution for the non-homogeneous case, but you're checking it in a homogeneous case. No, you want to check it in the non-homogeneous case. So doing that, we get 0 is equal to -A plus 40, and 0 is equal to A minus B plus 0. So that's just going to stay the way it is, right? So let me check. -A plus 40 and B, A minus B plus 0. So now we have that A is equal to B. And we have that A is equal to 40. So B is also equal to 40. So we can say that our particular solution is 40 and 40. So the particular solution, xp, remember that one does not have the constant in front, is going to be 40, 40. So now I'll show you later how to check the particular solution, which is similar to how we checked the complementary solution. Or actually, we could do it by hand, this one. So to check the particular solution, let's say we take the derivative of that. Well, that's going to be 0, 0. And I want that to be equal to -1, 0, 1, -1 times A, which is 40, 40, plus 40, 0. And I want 0, 0 on both sides because we have 0 on the left. So here on the top one, we can just keep them as matrices. So if we keep them as matrices, we're going to get -40 plus 0 and 40 minus 40 plus 40, 0. Which is going to be what? Well, we're going to have 0, 0, because these two become 0. And here we're going to have -40 plus 40. And this is going to be a 2 by 1, so don't get confused there. Because we also need the size to be the same. So we get 0, 0. And that is an identity, so that checks out. And so we're sure that this is our solution. Now find the specific solution using the initial conditions. So if we have the initial conditions, we want to go back to that form right there. So the general solution is going to be that x sub c plus x sub p, which is the complementary solution now is C1, 0, 1, e to the -t plus C2, e to the -t times 0, 1, remember the big bracket, times t plus 1, 0. That's it, right? If I factor out the e to the -t. And then we're going to add the particular solution, which is 40, 40. So now that we have this 40, 40, what we want to do is we want to solve for these. So we're assuming that this stands for a sub 1 of t, and this stands for a sub 2 of t. So what we can do is we can put 0 into a sub 1 and get 0. So this is going to be 0, and this is going to be 4. And remember, we inputted a t of 0, so we're going to have c1, 0, or let's just distribute that. So c1 times 0 is 0, so we're going to have 0 here, c1, e to the negative 0, that's just 1, plus c2, this is going to become a 1, e to the negative t, c2 times 0, well, actually we have a whole t here, so this whole first term will go to 0, and so we'll just have c2 times 1 and 0, and then we'll have plus 40 and 0. So now that we do that, we'll have 0 is equal to c2 plus 40, and 4 is equal to c1. So c2 is equal to negative 40. So right now we can rewrite what we had above, a sub 1 of t and a sub 2 of t, equaling c1, which is 4, multiplied by 0, 1, e to the negative t plus c2, which is negative 40, times e to the negative t, all multiplied by 0, 1 times t plus 1, 0, plus 40 and 40. And now I'll just go over to MATLAB in the last part to check whether this result is correct. I'll see you there.